Okay, what we're going to do, remember last time we got together before Thanksgiving. Hopefully you all had a really good Thanksgiving. Everybody have a good Thanksgiving? Yes? Just checking. No?
I had to put my mother-in-law in nursing home.
Oh, I'm so sorry. Well, how's she doing?
She's doing okay now.
Yeah.
She was taking more meds, which is supposed to be
Big adjustment, yeah. That's a tough thing to do, but hopefully her quality of life will be much better.
It will be. It was time.
Yeah. Well, I'm sorry that happened on that weekend.
It was on Thanksgiving Day. She
Wow.
decided to run the semi.
Ooh.
Yeah.
Wow.
Yeah.
Good for you for taking care of it.
Yeah. It was a busy weekend.
Well, what we're going to do today, the last time we met together we did probability. Remember I told you probability was a means to an end. We're going to backtrack and go back to standard deviation, which I just handed out to you, and we're going to review a little bit about standard deviation and then use it with those probabilities to do something else tonight. Okay? So, remember that we said the standard deviation shows the spread of the data, right? So that's what the standard deviation is showing us. Now, let's suppose that I was doing those aspirin bottle things, right? My little aspirin bottle. And I took my sample of, say, 20 aspirin bottles, and I found out that the average number of aspirin in the bottle is 248, and that it has a standard deviation of 2. Now that's a very small standard deviation as compared to the overall mean, okay? So that looks pretty good. But it's not 248. So I want to talk tonight about some of the things we can begin to do to use this information to make some decisions. Remember our plan was we had this population of 200,000 bottles, right? We took the sample of 20. We extracted this data of the mean and the standard deviation. We could test its quality by looking at the median and looking at the mean versus the median. We said the standard deviation should be less than half the mean, which it really is in this case, so that looks pretty good. But our goal was hopefully to be able to infer something about the 199,980 we had looked at. We're going to work right here today on this inference connection. We want to use the information from the data, from the sample, to say something about the population. We want to use the info from the sample to say something about that population, those items we haven't even touched. So again, in this example, we had 200,000 bottles. We took 20. And we want to use just these 20 to say something about all the rest of them. This is where the statistics becomes really useful and powerful and helpful. And we're going to use those probabilities that you guys worked on this last time in order to do this kind of inference. Now, if our data is normal, okay, so that's a big if, but if our data, I'll move this up so we can see it. Remember we talked about this when we did our stem and leaf plots? Remember that? We did exploratory analysis. We wanted, when you took the stem and leaf plot and turned it sideways so the stem's at the bottom, remember how we did the stem and leaf plot? If we turn that stem and leaf plot to the side, we wanted the data to look like this, right? Smooth, single-peaked, symmetrical. That means the two sides look identical. Okay, that's what we wanted to see. And if the data actually looks that way, if the data really is normal, then our standard deviation already tells us something about the population. Okay? If the data is normal, that's the big thing, if. Okay? If the data is normal, then if I take the mean and I add and subtract one standard deviation, I think we did this last time we met, but we'll do it. When we did standard deviation, I think we did this, we'll do it again. If I take the mean and I add 1 times the standard deviation, so my mean in this case was 248, and I'm going to add and subtract 1 times the standard deviation. My standard deviation here was 2, right? So I'm going to get an upper and a lower limit. I'm going to get a high number of 250, right? And a low number of 246, is that right? Correct? Right? So what I've done is I've formed an interval going from 246 to 250. So I've formed an interval on either side of that mean. Okay? Do you see that? This interval around the mean contains 68% of all observations. Everybody always asks, where does the 68 come from? It comes from those probabilities, those probability tables. If this thing is perfectly symmetrical, okay, has a perfect shape, then 68% of all the observations lie within 1 standard deviation. What that means in this case is that if these are the number of aspirin in the bottle, it means 68% of these bottles will contain between 246 and 250 aspirin. Now the 68 never changes. Okay? If the data is completely normal, 68% of all the observations lie within 1 standard deviation, always, no matter what it is, if the data is normal. If the data is not normal, this will be an overestimate. It will push your ends farther down than they need to be. If your data is not normal, this will make the interval larger than it really needs to be. So this is a very easy rule to use. A lot of people use this in all kinds of situations, in production situations, in determining costs, and doing all kinds of different estimates. If you need to come up with an estimate of something, and you know your average and your standard deviation, if you just take your mean and you go up and down 1 standard deviation, that's where you're going to, whatever your estimate is going to be 68% of the time or more. Because like I said, if the data is not normal, this is actually a bigger interval than it needs to be. The interval will actually be narrower. So this guy is going to give you a good, quick estimate. So if you wanted to know, for instance, you wanted to estimate the number of, the length of time it's going to take you to do something, like build a deck on somebody's house. If you know the average it takes you and the standard deviation, you can figure out 68% of the time where it's going to be. Or if you're trying to give somebody a cost estimate on something, if you know the average and the standard deviation, you can give them an estimate of where most of the time it's going to fall between this and this. Right? So it's a very good, I've seen people with production lines. They know their average number of units per day they produce and their standard deviation, so they know where they're going to be 68% of the time. So when the boss comes to them and says, I want to set a new rate, they know whether or not it's possible. Okay? So it's a really good, quick, easy rule to use to know where you're going to be most of the time. Now that's 1 standard deviation. Okay? If we go out 2 standard deviations, if we take the mean plus and minus 2 times the standard deviation, this is still if it's normal. Okay? So in this case we'd have 248, that was our mean. And we'll add and subtract 2 times the standard deviation. The standard deviation was what? 2. So we're going to have 248 plus and minus 4, right? So the top's going to be what? 252, and the bottom's going to be 244. Is that right?
We're getting 68%.
That comes from those probabilities that we had on those probability tables, and it's because of the symmetry. Remember how on those probability tables you were using the normal distribution is what you were using, the z-table is what you were doing, and you were finding one end or the other. What we did on this table is we went and found between, and we found between this point and this point where 68% of that distribution would be. So the 68% is because of the symmetry of this distribution, this guy. Because if it's perfectly symmetrical, then wherever its mean is, if you go out 1 standard deviation, this area, because of the symmetry, is always going to be 68%. And 68, like I said, 68% doesn't change. If you go out 1 standard deviation, you get 68%. If you go out 2, you get an area that contains 95%. 95% of all the observations lie within 2 standard deviations of the mean. Okay. So in this case, I'd say that these bottles of aspirin, 95% of our aspirin bottles contain between 244 and 252 aspirin.
And it would always be 68 from 95.
68, 95, yep, and there's one more. If you got 3, it'll be 99.7. 68, 95, 99.7. Go out 3, 99.7% of all the observations lie within 3 standard deviations of the mean. And again, it's just because of that symmetry. Okay. So of the 200,000 bottles we've made, 99.7% of them will contain between 242 and 254. Okay. I'll give you another example of how this rule is used. Suppose I was running this production line, and we're making bottles of aspirin, and we know that our average, we make 200,000 bottles a day, right? Per day. And let's say our standard deviation is 5,000 bottles. That's a big standard deviation. Let's say that's what it is. Well, 68% of the time, how many bottles are we going to make? Between 195,000 to 205,000, right? Right? What about 95% of the time, how many bottles do we make? 95% of the time we'd make between what and what?
190,000.
190 to 210. Okay, let's say the boss wants to set a new rate for us. Now what you've just told me is here's that distribution with 200,000 in the middle, okay? And you've told me 95% of the time we're going to produce between 190 and 210,000. That's what you've just told me. And 95% of the time you're going to be in that interval. Okay, what if the boss says, I want to set the new rate at 210. What are you going to say? If he wants to set the new production rate that you have to hit at 210,000 bottles. Now these are all come from probabilities. What's the probability you're going to make 210,000 or more?
5%.
You're close. Think again. You're on the right track. It's not, what, 2.5%? How'd you get that? You have the two tails, right? You have a tail over there, you have a tail here. So this contains 95%. That means there's 5% somewhere else, right? Split it in half, 2.5% up there, 2.5% down here. So if he wants to set the rate at 210, there's only a 2.5% chance that you'll make that or more in a day. What rate would you want the boss to set? 200 would be 50-50 chance with 200, right? Because it's right in the middle. If I were setting this and I could get any rate I wanted, I'd want the 190, right? Because there's only a 2.5% chance I'll fail, right? So I'd like to have the 190,000 because there's a 95 plus 2.5, 97.5% chance I'm always going to make that or more if I could set that rate. Because who knows, you know, people be sick, might not get all our resources, power failures, all kinds of things happen, right? Right? And so if you know what your average is, there's only a 50-50 chance you'll hit it, right? Now that's where these numbers come from. They come from these probabilities that you guys did last time. And what we'll do this week and what we'll do next week is we're going to use these ideas of probabilities again. But there's another interpretation of this rule. It's called the empirical rule. We could say 95% of the time we'll produce between 190 and 210,000 units. We could say there's a 95% probability that we'll produce between this and this. Or you could say, and this is one we care about tonight, I am 95% confident that we will produce between 190,000 and 210,000 bottles per day. I am 95% confident